This is the Building Automation Monthly Podcast with Phil Zito, episode 115. Hey folks, Phil Zito here, and welcome to episode 115 of the Building Automation Monthly Podcast. And in this episode, we are going to be finalizing the BAS optimization strategies two-part series. So what we covered in the previous episode is that we went through how important it is to make sure that everything is properly working. We went through the 5-step optimization process, and we talked through the difference between commissioning and optimization. Well, rather retro commissioning and optimization. So what we're going to be covering in this episode is we're actually going to be diving through 5 common optimization strategies that we're seeing utilized a lot in the building automation space right now. So it's really important that we point out the 2 things that you need to make sure are in place prior to any optimization strategy. The first off is that you need to have sensor accuracy. Pretty much every optimization strategy that you're going to implement where you're going about optimizing how you control HVAC sequences, those are going to be dependent on sensor readings. So if your sensor readings are bad, those optimization strategies can be programmed perfectly and still not work. So it's critically important that we do sensor calibration, which means we go around, we check our temperature, our pressure sensors, and we make sure they are calibrated. Now, calibration is an art form. I mean, it's not just going up to the sensor, taking your Fluke multimeter, sticking a 1K nickel probe next to the sensor and saying, oh, well, temperature is pretty much the same, so it's calibrated. It's actually going and testing the sensors through their operational range, or as much of the operational range as possible. So that means for humidity sensors, for CO2 sensors, for CO sensors, for airflow sensors, for pressure sensors, all of these sensors you want to go through the range as much as possible. Because what you don't want to happen is calibrating a sensor to the current measured value only to realize that there's an issue as you get towards the higher end or lower end of the range. You want to be able to move through the entire sensor range accurately. Now, what does that mean? Well, the sensor range, for example, the humidity sensor, that tends to be a 0 to 100% relative humidity, which corresponds to a 0 to 10 volt DC signal. So the range is 0 to 100% relative humidity. You would want to go about testing this. I'm not going to get into test procedures and test processes. That's something that you can easily type into Google. Just how do I calibrate? How do I test humidity, temperature, pressure sensors? You just type that in, you'll get so many answers and you'll get step-by-step processes, or you could type that into YouTube and get videos. That being said, sensor accuracy is key, but then we also have to have device accuracy. So our sensors are inputs, and if you've been following this podcast for any amount of time, you've probably heard me talk about the process loop, which is taking a value from a input, also known as a process variable, that goes into the controller. The controller then runs some logic to control that process variable to most likely a set point, and it controls that process variable. It modifies or changes that process variable by controlling an output. And this is where we need to focus on the second part, which is device accuracy. So you got sensor accuracy. Now you need to have device accuracy. Device accuracy is making sure that your dampers are properly mounted, making sure that your valves are fully stroking, making sure that as you move through these variety of things, valves, dampers, fan commands, etc., that they are actually reacting to the command they're getting, and they're controlling their controlled variable, whether that is a valve that is opening up to allow more water into a coil, whether that is a fan that has a VSD or a VFD on it that is ramping up. You want to make sure that these are accurate. These two things, If you don't do these and you implement an optimizing strategy on an existing building, you're shooting yourself in the foot. I am a firm advocate that before you ever look into optimization, you need to make sure that your sensors are accurate and that your devices are accurately controlling. If you don't do those two things, I know I'm hitting you over the head with this again and again, but this is so important. I've done so many service calls where the issue was simply an inaccurate sensor, a sensor that either wasn't properly wired up, or it wasn't properly calibrated, or there wasn't a proper offset, or there was a device that wasn't controlling properly, wasn't properly mounted, wasn't properly installed. And because of these two issues, no matter what optimization strategy you implement, you're not going to achieve your goals. So you need to knock those two things out first. Now, that being said, we have 5 optimization strategies that we're going to go through in this episode. I'm not sure how long this episode's going to run, but we will find out. So with that being said, our first optimization strategy is that we are going to go and look at the supply air temperature set point reset based on load. I know that's a mouthful, so let's dive into what that actually means. Okay. So supply air temperature, otherwise known as discharge air temperature, is the temperature that is leaving a air handling unit and is going downstream either to a space or to a series of VAV boxes. And so when we say set point reset based on load, the idea here is to say, all right, if I do not have a cooling load, if I do not have a heating load, whatever your load is, and typically supply air temperature set point reset is for cooling. But you look at your load, and a load is a cooling demand. So it's basically heat in a space or spaces. And you look at that load, and then based on that load, you're going to go and adjust your supply air temperature set point. Now, the theory behind this is that by reducing or increasing, so increasing would mean raising the temperature, that would be putting less load on your cooling system, or decreasing, that would be lowering the set point temperature, that would be putting more load on your cooling system. By looking at the spaces and saying, hey, there's not really a need for cooling, I'm going to go and reduce my supply air, or I'm going to increase my supply air temperature set point. So maybe from 55 to 60 or 55 to 65, I'm going to increase that. And by doing that, I'm cooling the air less. I'm taking less cooling draw from my chilled water plant. Remember in the previous episode, we talked about upstream, downstream effects. So I am now opening my valves less. If we have a variable secondary loop, then those valves closing down are going to increase pressure on the loop, which is going to reduce the speed of the secondary chilled water pump if you've got a VSD. And by doing that, you're having these kind of upstream effects of reduction of cooling demand to the chillers, reduction of pumping demand, reduction of a drain on your cooling capacity. That cooling capacity can be diverted to maybe other spaces that do have loads. So how you approach this, quite simply, is you look at load. But what is load? Now, there's kind of 2 schools of thought on this. One is to look at outdoor air temp. I'm personally not a fan of this because it doesn't take into account the building envelope. It doesn't take into account the solar gain on the building. There's a lot of variables. And plus, a lot of folks don't go and install the outdoor air temperature sensor in a good location. So depending on that to drive a supply air temperature reset is not the most accurate. It is one way, but it's not the ideal way. The ideal way is to look at space load. Now, there's 2 ways you can look at space load. One way is that you can look at damper position. If your VAV boxes are properly tuned, you can look at them and determine that there is a load based on when the damper goes past a certain percent. This would be called a call for cooling, which will be very important for you to remember when we move to item number 3, because call for cooling is going to be a very important part of how we go and use number 3's optimization strategy. So that's one way, right? The dampers being open. Another way is to look at the return air temp. That is where you look at a return air temp and you say, hey, based on return, I'm going to reset my supply air temp. If your return air starts to get really hot, that means that you have a increased load. Sometimes. That depends on if this return air is not being exposed to a hot plenum, it's not maybe running across a hot roof to get back to the unit. I mean, there's a variety of variables. That's why looking at the damper position or looking at the delta between set point and actual space temperature are two really good ways to go about calculating load. So what you do quite simply is once you've decided on those different methods, outdoor air temp, damper position, space temp versus set point or return air temp, once you've decided on one of those 4, then you quite simply take that value, put it into a span block. We're talking BAS programming now. And that span block then resets the supply air temperature set point. Pretty simple, pretty cut and dry. Moving on to number 2, you have hydronic set point reset based on load. This is another way of redoing or recalculating a set point so that you're either not heating the water or you're not cooling the water excessively. Now, this really shines in a primary secondary loop. It can also work in a solely primary loop as long as you have either fire rate control of your boilers or you have a set point control of your chillers. Let's talk about primary first because that's kind of the most simple one. So typically with a primary loop, what you'll have happen is you'll have 80% of the coils with 2-way valves and then 10-20% of the coils with 3-way valves. The purpose behind that is that you're allowing those coils with 3-way valves to maintain a kind of minimum flow. That way your chiller or your boiler has minimum flow going through it, which it needs in order to optimally control temperature. So as those valves start to close down, you are able to calculate a load if you know the load on the coils. Now, this is dependent on your coils not being fouled and a bunch of other variables. So some folks, instead of calculating a BTU load based off of valve position on coils, they will actually take the GPM of the loop. But this, as you're going to learn in a second, is dependent on something. They'll take the GPM of the loop, the delta T, the difference between supply and return, and they'll take that calculation times 500, and that calculation then becomes a BTU calc. And once you've calculated the BTUs, you can convert that to tons, especially on cooling. On hot water, it's a little different, but especially on cooling, you can calculate tons and then you can stage up and down chillers accordingly. So that's one thing. But what you can also do is, instead of staging up and down chillers, especially on a situation where you only have one chiller, maybe it's an air-cooled chiller and it's only primary loop, when you know the GPM, and this is dependent on having a variable speed drive on your primary, so that, because otherwise GPM is going to be constant, right? I mean, technically, you could still do this without a variable speed drive, because if you knew your GPM, your delta T would adjust, and that would adjust the load. But it's easier to do with a VFD because you have more, what's the word I'm looking for? More range. Your BTU range is going to be much higher. It's going to be more spread out, rather, because of the VFD altering the GPM. I know we're going a little deep here. If this stuff isn't making sense to you, I really encourage you to take my Control Sequence Fundamentals course, because if you're listening to the stuff and what I'm talking to you about is completely Greek to you, then that indicates that you've got a huge gap in your HVAC knowledge, and you need to close that gap if you want to have a successful career in BAS. There's no way of sugarcoating that. That's just the reality. Okay, so I mentioned valve position is one way we calculate load. The other way is that calculation where we look at delta T times GPM. But what do we do once we've calculated that load? Well, now we go into a span block once again, and we adjust our set point. Typically on chillers, we'll adjust anywhere between 42 to 52. On hot water plants, we can adjust, if they are non-condensing boilers, typically between 170 to 200, somewhere in that range, depends on a variety of different factors. If they are condensing boilers, you could drop a little bit lower because they will tolerate lower temperatures. That being said, once again, we can also use outdoor air temp, and this is what you'll often see. You won't typically see outdoor air temp with supply air temperature reset for air handlers. You'll typically see that reset based on zone, but on hydronic systems, you'll typically see set points reset based on outdoor air. And I really encourage you, especially with the fact that you're dealing with high BTU pieces of equipment that are either absorbing or transferring large amounts of energy, you really want to try to base that on load and not on outdoor air temp. That is really how you optimize your central plant. I've seen a lot of central plants that were driving themselves based off of outdoor air temp, and on kind of the transition days, it wasn't a heating day, it wasn't a cooling day, they were having issues maintaining set point because they were based on outdoor air temp, and there was still load, but based on outdoor air temp, the chilled water temperature was not getting cold enough to address the load because it was simply based on outdoor air temp. All right, so this next strategy is a little bit complex. It's something I cover in my programming course, and I had my students in my programming course, one of them, actually a couple of them, asked me, why do you teach this? Why did you teach this form of pressure reset? And I taught it because it's a very common sequence that I'm actually seeing pop up a lot more lately. And that is called trim and response based on demand. Essentially, what you do is you've got a discharge air static pressure set point, and you look at and this is traditionally used with VAV systems. So you've got an air handler with a VFD on the fan, on the supply fan, and you've got VAV systems downstream of the air handler, and they are opening and closing their dampers. And what happens is when the supply temp, or when the space temp gets above the space temp set point, at a certain point, a comparator will be triggered, and that's a programming logic block once again. A comparator is triggered, and that triggers a call for cooling. What you do is you look at these spaces and you add up these calls for cooling. And if you have a certain amount of calls for cooling over a certain period of time, you gradually increase your discharge air pressure set point. The theory being that these boxes are starting to open up, but yet they aren't going and achieving temperature control of the space. Thus, you need to supply them more cold air. Now, there's a huge assumption made with the trim and response based on demand. And I've seen this get kind of wacky, to be honest. I see folks go and use supply air temperature set point reset and trim and response at the same time. And sometimes, if not properly calibrated, these two can actually fight against one another. The theory behind trim and response is that you keep the temperature right around 55 degrees. And that temperature then is supplied to the space. And you are going and optimizing by varying the flow. Less flow through the coil means that less BTUs are being transferred to the airstream. So thus the trim and response is optimizing by either increasing or decreasing pressure, which in turn is going to go and provide more or less air to the space. Now, as I mentioned, you can do that based off of a call for cooling, which can be a set point space set point compared to space temp. You can also do this by looking at damper position. This is another way of doing trim and response, which is one of two things. You either have a comparator in the local VAV program, comparators once again being a logic block, and that comparator is saying if damper position is above a certain percent for a certain amount of time, this triggers a call for cooling. And once you get enough calls for cooling at your air handler controller, your trim and response takes effect. Another way of doing this, however, is going and looking at average damper position. So there's two schools of thought on this. One school of thought is that with the comparative method, then what you're able to do is with temperature, you are now relying on actual load. The downside of looking at temperature is if there's an issue with your box, you could be artificially increasing the supply airflow set or supply discharge set point because this box isn't opening. That could be an issue for you, and you don't want to experience that issue. That issue can really cause some problems. However, at the same time, if you're looking at damper position and the damper's driving 100% open, but the damper physically isn't open, that once again is another issue. Now, this all goes back to why I said you need to make sure your devices are accurately calibrated and controlling prior to optimization. You can see how you can really screw things up if you don't do that. That being said, that is why some folks will go and they will use a call for cooling method rather than an average percent or simply looking at a temperature set point. They will do a call for cooling based off damper position, but if they see that there's 0 CFM and the damper's at 100, that will create a flag called out of service or device failure or failed damper or whatever, and that flag will keep that call for cooling from passing to the trim and response. Now, that was a lot to take in. I realized that was a deep concept. So let's revisit that real quick. Okay. So you have these VAV boxes, and these VAV boxes have three ways of saying that they're calling for cooling. One is the difference between space temperature and space temperature set point. The other is the damper position being greater than a certain percentage. And the third is calculating the average of the damper positions. All three of those scenarios, you can still throw out bad values by looking at 0 CFM or very low CFM and damper position. This is a real simple AND gate with two comparators. You say, if damper position is greater than a certain percentage and CFM is below a certain value, then say that the box has failed and throw that value out. So trim and response acts by going and trimming and then responding. So pretty simple, pretty basic sequence. I know for some of you, you're like, hey, that's not basic. Once you've done this for a while, you start to see that these are fairly standard optimization strategies. Now, the fourth bucket is economizer optimization. And economizer optimization, first off, what is economizer? Because you may not know that. Economizer is simply a fancy way of saying the outdoor air damper. Okay, so basically what you do with the economizer is you are going and saying, hey, if the outdoor air temperature is at its most basic level, if the outdoor air temperature, the dry bulb, is below a certain temperature, but above another temperature, we're going to open up the economizer and let the economizer either control to mixed air temp or control to discharge air temp. So that is one way, and that's the way we're going to focus on. And then I'll talk about enthalpy, and then I'll talk about return air compared to outdoor air, and then we'll talk about mixed air. Okay. So what you can do in its most basic form is you have economizer lockout, typically set somewhere like 65 degrees. If it drops below 65, but it's above 48, you open up your economizer and you allow your economizer to control to discharge air temperature set point. And so it will typically control to maybe 2 degrees above discharge air, because you don't want it to overshoot. If you've got a tightly tuned loop, you can actually control to discharge air temp. Another way of doing this is controlling to mixed air, which we'll talk about in a second. So you open up the economizer, it's got a PID loop that controls it, and it drives to the discharge air set point. That's all dry bulb. Then you have enthalpy, which is essentially you're looking at the energy that's in the air. Because remember that moisture in the air contains BTUs, and the higher the relative, so a relative humidity of 80% at 90 degrees is a lot more moisture than a relative humidity of 80% at 50 degrees. Because as air gets warmer, its capacity to hold moisture gets higher. That is why you see that folks are feeling really muggy at 90 degrees, 80% relative humidity, but 55, 80 is not as bad, because essentially you have grains per pound of moisture. If you've ever looked at a psych chart, it's that vertical line on the far right side of the psychrometric chart. If you haven't gone through psychrometrics, really encourage you to. That's another thing I cover in my control sequence fundamentals course. It is a vital skill to understand how to read psychrometrics. I've troubleshot so many issues by just understanding psychrometrics and going, there is no way this could possibly work because it defies the laws of psychrometrics. And so understanding psychrometrics is going to really help you out. But essentially what you're doing is you're looking at the amount of BTUs that are in the outdoor air compared to the amount of BTUs that are in the return air, and you're deciding, does it make more sense to cool the return air, or does it make more sense to cool the outdoor air? Because if you bring in heavily moisture-laden outdoor air, then what happens is the cooling coil has to work really hard to, once it hits saturation, drain all that moisture out of the air and go and lower the temperature. So by being aware of enthalpy, you are making the decision, what is going to take more energy for me to cool down some maybe warmer but much drier return air, or for me to introduce all this humid air into my system and have to flush that out? So that is another way of economizer optimization. As I said, there's many different ways. Another way is just looking at outdoor air versus return air temperature. That's another way. It's not as accurate as enthalpy. I really don't suggest using that method. There's really no point. If you're going to compare return air, you need to do enthalpy comparison, and that's the way to do that. Otherwise, just drive it off of dry bulb for outdoor air. And the final way is, whether you're driving off of outdoor air, dry bulb, or enthalpy, is instead of controlling the discharge air temp, you control the mixed air temp, and you can actually go and maybe control a little bit lower and take advantage of reheat, which is not as efficient, but is one way of doing it. Or you can control to maybe a little bit higher with mixed air temp and be willing to say, hey, I'm not going to have as low of discharge air temp, but that's okay because I am going and saving energy. It all depends on your strategies here. So that's our fourth optimization strategy. And our fifth optimization strategy, and this is something that I find a lot of new techs don't realize, and it's optimal differential pressure sensor placement. This is not so much of an optimization strategy from a sequence perspective as much as it is a installation strategy that has a dramatic effect on system performance. If you ever go to a site and it seems like the pumps are just running crazy or the fans are running crazy, your PID loops, despite your best efforts to tune them, it just seems like the response is crazy fast, then you most likely have a differential pressure sensor placement issue. You could have ramp rate issues on your VFDs. You could have issues on your PID loops. But if you've addressed those two things and you're still getting where the pump is just crazy responsiveness, I mean, it's just up, down, or the fan's doing that as well, then you most likely have DP sensor placement. Because what we have to realize is that, let's break this out into water, hydronic, and air. So we'll do air first. So the rule of thumb is 2/3 down the duct, right? You want to go and you want to put your DP sensor 2/3 down the longest duct run. And that's all well and good. But what if down the longest duct run is actually a really poor sampling of boxes? What if most of your boxes are, I was about to say 10,000 CFM, that'd be huge, are 1,000 CFM, and your box or boxes that are by your DP sensor are 200 CFM. They're not representative of the system. So by putting your DP sensor where it's not representative of the system load, you are going to have a much more dramatic effect. You're going to be ramping up and ramping down. So what you want to do is put in air side systems, you want to put the DP sensor near the greatest diversity of load, because you want that response as those really big boxes or the blend of boxes close down. You want that DP sensor to sense that effect. And if it doesn't, and so you could do this, a couple different ways. You could do this by averaging. You could put DP sensors in multiple different spots and average that. That's one way. You could do this by putting it into a place where you have a diversity of box types. You can do it multiple different ways. The important thing is to not let a DP sensor sit with a 200 CFM box when you've got 20 boxes that are 1,000 CFM. Does that make sense? Is that kind of clicking why you would want that? Because that box, that 200 CFM is going to close down, the pressure is going to build up, and that DP sensor is going to start to cause the fan to ramp back. You could have starving boxes at those 1,000 CFM boxes. Well, also on the hydronic side, we want to have our DP sensor ideally as far down the pipe run as possible, because we want to go and keep a low DP setting, meaning that we want to run the pump as low as we possibly can to maintain the differential pressure. Because as differential pressure builds up, we are going to go and back up our fan, and then our valves, our pump, and then our valves are going to open up. So if we put our differential pressure right in front of the pump, which I've seen folks do in the past, then you're going to have that pressure build up because it hasn't dispersed through the system. And that is going to cause your pump to cycle down because pressure is going to build up, and it's going to cause a roller coaster pump. Versus if you push it further down the line, you're having an opportunity for that pressure to kind of settle into the system, and you're giving that pump a longer delay between the change in pressure and it increasing itself, because the valves are going to adjust as well. When the pump starts to ramp up, the valves ideally should close down, and as the pump starts to ramp down, ideally the valves should open up. As valves open up, differential pressure drops. As valves close down, differential pressure increases. So that is why you want to have your differential pressure sensor further down the system, so you can see a greater accurate reflection of what the differential pressure is within that piping system. Okay, so we covered a lot in this episode. We went through a lot of deep concepts. Let's recap real quick. Step 1, sensor accuracy. Step 2, device accuracy. Those are a have to have prior to doing any optimization. I've given you 5 optimization strategies that pretty much anyone with about a year, a year in the field, a couple months programming should be able to accurately implement. If you've gone through my programming course, you're going to learn all of these different design patterns associated with these kind of optimization strategies. So with that being said, the 5 optimization strategies we went through are supply air temperature set point reset based on load, hydronic set point reset based on load, trim and response based on demand, economizer optimization, and optimal DP sensor placement. These are all very important for you to understand. If you're not understanding the HVAC aspect of this, I cannot emphasize enough that you should go through our course on control sequence fundamentals. It's important to invest in yourself and invest in your career. What I would like to hear from you, I'd like to hear the optimization strategies you're using. So go leave a comment in the comment section. Everything that has been discussed today can be found at buildingautomationmonthly.com/115. Once again, that is buildingautomationmonthly.com/115. Thank you so much for being here in another episode, and I can't wait to talk with you again next week. Until next time, take care.